Concept 52.1 says Earth's climate varies by latitude and season and is changing rapidly. Now, if you've had the advantage or the good luck to be able to travel to any degree, you know that the entire world is not like Waxahachie, Texas or Tyler, Texas. There are variations even in our own country. Our own country is very large. So if you travel down to the coast of Texas, that's quite different from Waxahachie or Tyler. And then if you travel to other parts of the country, like you go out to Los Angeles or you travel up north to Chicago, you'll see quite a bit of difference in weather conditions and climate and land and animals. And then if you're really lucky and you've been able to travel around the world to other parts of the world, say Europe or Africa or South America, certainly you see quite a few differences. So let's talk about some of the weather and climate conditions that make the Earth different, and then of course that affects the different living creatures that are in that part of the world. The first thing we want to talk about is this word climate, and of course that's been around in the news quite a bit over the last 10 years because of some of the changes that our climate, the Earth's climate overall is going through. Climate is the long-term prevailing weather conditions of a particular area. So when we talk about climate, we're not talking about the fact that it's rainy today or cold next week. We're not talking about the day-to-day weather conditions. We're talking about a long-term, big picture idea. If you look at the weather conditions in Waxahachie over the last 100 years, well, that might help you understand the climate of our particular area. So 4 major abiotic components. Abiotic means non-living. 4 major abiotic components of climate are temperature, precipitation, which that would be anything basically falling from the sky. That would include rain, snow, sleet, hail, sunlight, and wind. These 4 combinations of factors help determine the climate of an area. In the news lately a lot, they've been talking about global climate change or global warming. That would certainly be macroclimate, macro meaning large scale. Macroclimate consists of patterns on the global, regional, and landscape level. So we're talking about big swaths of land or large areas. We could also talk about microclimate. Microclimate would be very fine patterns in very small areas. Like you could look at the microclimate that exists underneath a fallen log in an East Texas forest. And the microclimate underneath a falling log in East Texas forest is going to be different than the microclimate at the top of a pine tree in an East Texas forest. So you could get very small, or you could look at the entire world, the global climate, and that would be macroclimate. If we want to zoom out and look at the entire Earth and talk about global climate patterns, for the most part our global climate is determined by the amount of solar energy our planet receives and the planet's movement within space. And the warming effects of the sun causes temperature variations, and the angle of the sunlight as it hits the Earth causes variations. Different parts of the globe get more direct sunlight than others, and that causes changes in evaporation. It helps develop wind patterns and circulations of air and water, and this is what causes the various latitudinal variations in the climate. In other words, if you start in the middle at the equator and work your way up horizontally toward the North Pole, or you work your way down horizontally toward the South Pole, that's a latitude, and that latitudinal difference is mainly described by the amount of sunlight and the various weather conditions caused by the decreasing or increasing amount of sunlight. If you want to look in your textbook on page 1146, they've got some good information there and some good pictures to take a look at. So the latitudinal variation in sunlight intensity is really what causes our global weather and our global climate. You know, the Earth does not receive an equal amount of sunlight over its entire sphere. The angle at which that sunlight hits affects the amount of energy that's imparted by that sunlight, and that affects the amount of heat and light per unit of surface area. Of course, around the tropics and the equator, that's where the light intensity is the greatest. That's where the angle is the most direct, and so that's where you're going to get the highest concentration of energy, and that's going to be, again, you could probably guess, going to be where the warmer climates tend to be. So here's a good picture showing if we were talking about the equinox, which in the spring and in the fall we have a point at which the sun hits directly over the equator. And so at the equinox you have a most direct point right there at the equator, and then that sunlight is hitting at more and more of an angle as you go north or south toward the poles, because of course we live on a sphere, and so we don't get the same angle of the sunlight at this part of the sphere as we do right in the middle where the sun is hitting directly. So this change, it doesn't seem like much, but that change, that direct hit at the equator there, imparts a tremendous amount of energy, a higher amount of energy than the angled energy here at the poles. The amount of light is spread out further, covering more land, and here it's more concentrated there at the equator. The fact that the sunlight provides different amounts of energy on different parts of the planet, that is what affects our air circulation and precipitation patterns for the entire globe, and that's what affects the overall climate and the weather that we see. Water evaporates in the tropics near the equator faster and at a higher rate, and that warm, wet air flows toward the poles and then drops as it gets colder or higher, and these massive convection currents are responsible for the ever-changing weather patterns that we see. So we'll show you a good picture in just a second right here. Here at the equator we can see right there along the edge they show these weather patterns, these convection currents. Hot air, the hot, warm, humid air rises from the equator, travels up toward the poles, and as it rises it starts to cool, and then of course as it goes north or south it also begins to cool, and then it falls. And we basically have 3 of these large convection currents toward the north and 3 of these large convection currents toward the south. And this hot warm air rising and colder drier air falling, these currents help create the weather patterns that we see on a regular basis. So the rising air masses, they begin to cool. As this rising wet air from the equator rises, it begins to cool off, and so it has to release that water, drops that water out, and causes high amounts of precipitation, especially in the tropics, the areas just north and south of the equator. Then the dry descending air creates arid climates, especially near 30 degrees north and south. And the air flowing close to the Earth's surface creates predictable global wind patterns. If you've ever watched the Weather Channel, you know they talk about things like the jet stream and the trade winds and the westerlies. Well, these are particular wind patterns that are pretty steady, and they remain for the most part fairly unchanged. Trade winds blow from east to west in the tropics, and then prevailing what we call westerlies blow from west to east in the temperate zones. So again, we'll go back to our map here and take a look at what we're talking about. So here you have the trade winds that for the most part blow from east to west, so you can see east to west right there, north and south of the equator. And then going up one more, sorry about that, going up one more we have what we call the westerlies, and the westerlies blow for the most part from the west toward the east. And this is not a pattern in every, sorry, I keep hitting the wrong, trying to work with my trackpad there. This is not a pattern that is maintained always, 100% of the time, but for the most part, this is the basic wind conditions and weather patterns that you see. So you'll see specific bands of wet weather in certain parts of the world, and specific bands of dry, more arid weather in different parts of the world. And it's because of these large currents that you see here, these large global air patterns that are caused by the amounts of sunlight that the Earth receives. So we could also kind of zoom in closer and talk about certain parts of the world, regional and local effects on climate, and that's going to be affected by our seasons as well as large bodies of water and mountains. So if we zoom into a certain part of the world, we can talk about what affects the weather in that particular part, or what affects the climate in that particular part. The first thing we want to look at is seasons. Of course, you know, even in a place like Waxahachie or Tyler, Texas, we have colder winters and warmer summers. We don't get a huge variety, although we do have some pretty hot summers, well over 100 degrees. And you notice we never really get down below about 20. It's pretty rare for us to get below about 20. We don't have a huge amount of, say, snowfall in the winter. We get a small amount sometimes, but not a huge amount. Well, these seasonal changes is because of the variation of energy that we receive from the sun as the Earth travels around the sun. So if you want to see large changes, you go toward the poles, because toward the poles the angle of sunlight is greater, and so the differences between weather in, say, the summer and winter tends to be fairly great. There's a large amount of variation. If you don't want to have a lot of variation, if you want to retire to a place where it's always 75 and nice and warm and sunny most of the time, you would go to the equator. So you might go to the tropics where you would get a lot more rain, but for the most part it's never going to get much higher than 80 or 85, and it's never going to get much lower than, say, 65 or 70. You're not going to see the temperature extremes at the equator because they consistently get the same amount of energy. So we can look at different parts of the world and the seasonal changes, and if you want to go to a place where it doesn't really matter if it's winter, spring, summer, or fall, you go to the equator. And if you want to see big differences, you start to go away from the equator toward the poles. You guys are at the very end of your high school career, so I would certainly hope that you have a firm understanding of what causes the seasons here on Earth, and I would never want you to think, like a lot of people still think, that it's the distance from the sun. A lot of people tend to think that, well, in the wintertime we're farther away from the sun, and in the summer we're closer to the sun, and that's not true at all. We live in North America, we live in the northern hemisphere of the Earth, so if that were true, if we were closer to the sun in the summer and further away in the winter, well, that you would have to explain a few things that go on in the southern hemisphere as well. For example, if your explanation is that, well, in the winter the Earth is farther from the sun and that's why we're cold, well then you would have to explain to me why when it's winter in Waxahachie, Texas, people in Australia are celebrating Christmas at the beach and they are sunbathing and having picnics and barbecuing and getting sunburns. Well, that's because we're not farther away, or at least that's not what causes the weather conditions. That's not what causes the seasons. As a matter of fact, the Earth is slightly closer to the sun during our northern hemisphere winter and slightly farther away during our northern hemisphere summer. But that's not what causes the seasons at all. It's the tilt of the Earth that causes the seasonal change as we move around the planet. So in our summer, we would be tilted, our portion of the world is tilted most toward the sun, and notice the northern part of the planet is getting the most direct sunlight. In March and September we have what we call the equinox, and the sunlight, sorry I keep doing the same thing, and the sunlight is most hitting flat on at the equator there. Now in December, notice our part, the upper part of the world, the northern hemisphere, is tilted away from the sun. So it's the tilt of the Earth that causes the seasons, not the distance from the sun. So in our winter here in December, you notice the people in the southern hemisphere down here in Australia, they are tilted more toward the sun, and that's why for Australians Christmas time is a beach holiday. You go to the beach, you suntan, you hang out at the pool. For Australians, Christmas time is always a shorts and t-shirt kind of holiday, and it's because when we're tilted away, they're tilted toward, and of course vice versa. For them, June, July, and August are the coldest months of the year because the southern hemisphere is tilted away in what we call our summer. So again, every intelligent adult should understand why Australians have Christmas at the beach and what causes our seasons. Now if we zoom into a particular part of the world, we can talk about certain things that affect a particular portion of the world. Like if we go down to Corpus Christi, Texas, or you go out to any city along the coastline, you'll notice that their weather doesn't change quite as much as far as highs and lows of temperature. And if you live near, say, one of the Great Lakes, like say Lake Superior, or you live near the ocean, you're going to find that big chunks of water have an effect on your weather. We have something called the Gulf Stream. The Gulf Stream carries warm water from the equator to the North Atlantic throughout the ocean, and these large bodies of water can have an effect on the climate of the land nearby. So if we were going to look at the entire ocean, you see these large currents called gyres, and there are about 4 or 5 large gyres within the world's oceans, and they've actually named them the Indian Ocean Gyre, the California North Pacific Subtropical Gyre. These are basically giant currents of water slowly moving over time, carrying warm water, mixing it with cold water, and that water and that movement affects the land temperature and climate near it as well. A good example is what we call a sea breeze. If you've ever gone down to the coast and you notice there always seems to be a breeze, it's always kind of windy down on the coast. And here's what happens. During the day, the land heats up faster than the water. So the air over the land rises quickly, and you have cooler air coming from the ocean to kind of replace that air that left. So during the day you have this effect where you have a cooling breeze coming from the ocean toward the shore, and during the day you'll notice that the wind always seems to be coming from the water toward the shore. Now as night falls, what happens is the land cools off more quickly, the water holds on to that heat, and you have the exact opposite occur. You have the air over the water is still more warm and it rises, and then you have air from the land going to replace that. So if you ever go to the beach, if you spend say spring break at the beach, you want to try to notice this. During the day you'll notice the breeze always seems to be coming from the water toward the land, and at night you'll notice the breeze always seems to be coming from the land back towards the water. And that's because of the water and land difference as far as how quickly it heats up and cools down. Water is a very good has a very strong ability to hold on to thermal energy, so it takes it much longer to heat up, but it also takes it much longer to cool down. Something else that can have a big effect on local weather conditions or climate is mountains. If you've ever lived, don't have a lot of mountains here in Texas, but if you've ever lived in a mountainous area, California, out near Seattle, that type of area, you'll notice that the mountains have a big effect. On one side of the mountains it tends to be very rainy and wet and very lush, and on the other side of the mountains it tends to be pretty dry and arid and kind of desert-like. And that's because of what we call a rain shadow. And we'll take a look at a picture and it'll kind of help explain what we're talking about. So this would be, say, like the west coast, like the Seattle area. You have the warm ocean airflow coming this direction. It contains a lot of moisture. As that moist air rises to go up over the mountains, it gets to the cooler parts of the atmosphere, and that water condenses, drops as rain. So on this side of the mountain, the leeward side, I'm sorry, the headward side of the mountain, you have large amounts of rain that fall, and this side tends to be very lush with vegetation, higher amounts of rainfall. And if you've ever gone to Seattle or the state of Washington, you know the coastal areas toward the west tend to be very much like that. They are a rainforest type condition. Now on the other side of the mountain, all that air has dropped the moisture that it was containing, so as it comes back down, it's very dry, very cool and dry. And this side, the leeward side of the mountain, tends to be very desert-like. And again, in Washington State, it's a great example. If you go the western part of the state, it's very kind of lush and almost tropical, temperate, tropical rainforest. But if you go to the mountains and over the mountains to the eastern side of the state, you'll find it's very dry and almost desert-like. And this is called the rain shadow. All that moisture gets dropped here as the air rises, and then there's no moisture left on the other side. So the mountains affect not only the rainfall, but they also affect the amount of sunlight that hits a particular area. In the northern hemisphere where we live, a south-facing slope receives more sunlight than a north-facing slope, and so you'll see differences in the plants and animals and weather conditions for one side of the mountain as opposed to the other. And then again, elevation plays a part. You know, the higher you go, the cooler it gets. So for every 1,000 meters increase in elevation, you're going to have a temperature drop of about 6 degrees Celsius. So the higher you go into the mountains, the colder it gets, and of course the lower you are down on the mountain, the warmer it is. So something like a mountain can also affect the climate of a particular area and a particular ecosystem. Again, if we want to zoom in to one particular tiny area, like we could look at the microclimate in your backyard, or we could look at the microclimate, again, like we mentioned, underneath one rotting log in an East Texas forest. Microclimate is kind of the same way, but you're just looking at it at a much smaller scale. It's affected by light and wind patterns and rainfall, just like the large macroclimate is. But we have to look at the abiotic factors, the non-living parts, temperature, light, water, nutrients, as well as the biotic, the living parts like the other living creatures that are part of that environment. So you can zoom in and you can talk about the weather conditions or the climate of one tiny little area. You could talk about the corner of your backyard, and maybe there's one particular sort of little ecosystem. Maybe it's in a pile of leaves or in the top of a tree. That would be the microclimate. One last thing to mention in this particular chapter area here is global climate change, and of course that's been in the news quite a bit, and there is some controversy in non-scientific circles. I will tell you, among scientists who study the climate and study weather patterns for a living, there's very little controversy. The vast majority of scientists who study climate and weather conditions for a living will tell you certainly that the global climate is changing, and it seems to be changing more rapidly than in past instances. And there certainly seems to be ample evidence that human activity is playing a role in that. So when you hear about the controversy of global climate change, I want you to understand that for the most part, that's like the controversy of evolution. It's not really a controversy. It's not a controversy amongst the scientists who spend their lives studying this information. It may be a controversy among people who do not study this particular science for a living, but that's different. That's kind of society and political, and it doesn't really have to do a lot with the actual science. So what is the big deal about this? Who cares if the global climate changes a few degrees? How could that possibly have such a big effect? Well, changes in the Earth's climate can really affect the biosphere, the living creatures, and they have a particular range that they do best in, and when that range shifts, sometimes the creatures themselves can't adapt or shift quickly enough. One way to look at how this might affect our future is to look at the past, so to study previous climate changes where the Earth has gone through ice ages and warming periods and things like that. And certainly that there is a natural cycle of the Earth warming and cooling, the climate changing over time, and that's not in doubt. The climate change that we're going through right now may be in part affected by these normal changes, but there are also big components that point to the fact that human activity is playing a part in this as well. So for example, as the glaciers retreated 16,000 years ago, there was climate change, and different plants and animals had to adapt and change their habitat, their environment, the area that they lived in. And the problem is sometimes the changes in climate occur faster than the animals can change and adapt and move into a new range. And when that occurs, you're going to have pretty large extinctions, and you're going to have creatures and populations that get wiped out. So for example, we could look at how the climate change might affect the range of a particular type of tree, and we can do some predictions based on what we've seen in the past as well. And again, the problem is, can these creatures adapt and change and shift their habitat quickly enough? Sometimes they can, sometimes they can't, and if they can't, they're likely to go extinct. Alright, we're going to take a quick break right there. When we come back, we're going to look at terrestrial biomes. So we're going to look at land-based biomes like deserts, grasslands, forests, the different parts of our world basically. If we start to zoom in and divide up the entire Earth into different ecosystems or different biomes, we want to look at the different ones that exist. That would be Concept 52.2. We'll be right back.